Hi again, and welcome back to the second part of Lecture 8. In this one, we're going to take a look at stars and stellar populations in early type galaxies. We're also going to have quite a strong emphasis on the kinematics, the internal kinematics of early type galaxies, because early type galaxies do not contain a lot of gas, and in particular not a lot of dense neutral gas. And that means that the internal motion in these galaxies, the internal kinematics in these galaxies, is dominated by the collisionless dynamics of stars and dark matter particles. In contrast to star-forming galaxies, where there is a lot of neutral dense gas, in particular in the disk, which means that the motion there, the internal motion, is dominated by the collisional dynamics of these gas clouds. And that means that we see some very, very different phenomena, some very different kinematical patterns in early type galaxies compared to late type galaxies. And that's what we're going to try and also take a look at here. I have to say straight away that this is a huge topic, like entire careers have been dedicated to researching this field. So we will only be able to scratch the surface very superficially here, but we will try and pick up as much as we can. So stellar dynamics in early type galaxies is based mostly on absorption lines. This is just practical. First off, there isn't a lot of gas that can give us emission lines, and there aren't a lot of emission lines in stellar atmospheres. So typically what we have to work with is absorption lines in the spectra of stars in these galaxies, or more typically in the integrated spectra of these galaxies, or in the integrated spectra of parts of these galaxies. The typical classical old school way to characterize the kinematics of galaxies is by using long slit spectroscopy, as we can see here. And I need to apologize in advance that I could only find an example online that was using a spiral galaxy, but it works the exact same way if we had been looking at an early type galaxy. So what we would do would be to place a spectroscopic slit across the galaxy, and then from here, from the emission lines, but in an early type galaxy from the absorption lines, map the red or blue shift of these of the stars in the galaxy, or in this case the gas, as a function of its position along the slit. So down here we can see some very conspicuous, some very strong emission lines. I believe this would be H alpha and the surrounding nitrogen doublet here, and down here we will see the singly ionized density sensitive sulfur doublet. In any case, that's not relevant for early type galaxies. The main principle that we need to look into here is that we can see that there is a shift in the centroid of the lines. We should remember that what we're looking at is this here. So the vertical axis here is the wavelength axis, and the horizontal axis is the spatial axis along the slit up here. So as we move through this galaxy here from a higher radius and in towards the center, we see that the light becomes less and less blue shifted, and then it shifts rather rapidly around the center, and then it becomes slightly more red shifted, but settles at these more or less constant velocities that we have seen in previous lectures. And what we will do in order to characterize an early type galaxy is that we will use its central velocity dispersion, which is basically the width of the absorption lines that we see in the central area of the galaxy, together with its rotational velocity, which is basically the maximum rotational velocity that we see here, and use that to characterize how dominated this galaxy is either by rotation or by internal velocity dispersion. And we can then use this to classify ellipticals into so-called fast or slow rotators based on the relative strength of these quantities that we're looking at. In more modern times, we have, with the advent of so-called integral field units, made it possible to actually take a full spectrum for every pixel in an image of a galaxy. And that, of course, means that we can map these kinematical properties with much higher detail, much more accuracy, and much more refinement than we would be able to do with the old school version that just used a single long slit or maybe a couple of long slits across the galaxy. So here we have two examples. You can see this one on the upper part has a velocity shift from here where it's about minus 280 kilometers per second, and here it's plus 280 kilometers per second. So quite fast rotation, right? You can also see here that the velocity dispersion in the center comes up close to 250 kilometers per second, but out in the outskirts is much lower, maybe around 100 on average kilometers per second. So that means that the maximum velocity here will be around just under 280 kilometers per second, and the central velocity dispersion will be around, I don't know, maybe the same-ish, I'm not sure. So this one has a ratio of these two things of between 1 and 2 maybe. Looking down here, we see that this one is rotating much more slowly. And on the other hand, the central velocity dispersion is not that different from the upper one. So this one is by far more dispersion dominated. It's a much slower rotator than the first one. We can also see, which I just want to point out, that in the lower galaxy, in the outer parts, we can see a velocity gradient from the upper right to the lower left, whereas in the inner parts, we can see another velocity gradient, which is almost at a straight angle to it, so almost perpendicular to that, right? This also, again, could show us that there's a lot happening inside these galaxies kinematically, and this is what we would call like an independently rotating, an independently moving core galaxy. More quantitatively, the way we do these classifications is by using either what we call V over sigma method or the lambda RE method. And these are basically just different ways of quantifying the importance of rotation versus the importance of internal random velocity dispersion. One we can use is this one that's called the V over sigma. And in the old school versions, that is basically just using the maximum velocity as V, but in newer IFU-based studies, we have a slightly more refined, complicated definition of what this ratio is. Also, we don't necessarily just use the central velocity dispersion anymore, but rather use a brightness or luminosity weighted velocity dispersion, because we can measure the velocity dispersion in every single position now, and then we can weigh that by how bright the galaxy is in that position, and then we can use that as our measurement of the internal velocity dispersion, such that brighter parts weigh more heavily, but they are not the only thing that goes into the equation. And in the bottom, we have this method here that's called lambda RE, which is, well, this is this thing here. That's the definition of it. You can look more into it in the course book. In practice, so this here is a measurement that is done in isophotes or like in bins of isophotes in principle, but in practice, what we will do is that we will basically just do these measurements in the individual pixels of an IFU observation instead. And once we have these quantities, we can then plop them into a diagram like this. Here you can see a V over sigma plotted against the ellipticity of galaxy, and here you can see lambda RE plotted again against the ellipticity of such a galaxy. And here you can see that we have a separation between fast rotators and slow rotators, basically based on their on the ratio between the rotation velocity and the internal velocity dispersion. Typically, we will use a value of around 1.6, 1.7 as a cutoff between fast and slow rotators. That is kind of like a quick and dirty way to classify them that way. But as you can see in this diagram, people have also classified them in other ways by other means. I do not know exactly how they're classified in this diagram, but they are. Actually, I would guess that they're classified by the lambda RE method. As you can see that this curve here seems to exactly completely split up the population between slow and fast rotators. So I guess that it is just this classification which has been carried over into the diagram over here. As an example, we can take a look at this spectrum here from a long slit spectrum from an early type galaxy. This is from a different book than the one we're using now, but I think it's a very nice and instructive example. So here you can see measurements of both the velocity dispersion and the radial velocity along a number of bins along slits placed on top of an early type galaxy. And what we can see here is that we have a velocity dispersion in the center, which is around 400, but a luminosity weighted velocity dispersion, which is probably closer to around 250 kilometers per second. It doesn't matter that much exactly what the number is, because we can see that compared to it, the rotational velocity is no more than maybe 35 kilometers per second. So this is definitely not a rotation dominated galaxy. This is definitely a velocity dispersion dominated galaxy. That is, it is dominated by random stellar orbits rather than ordered motion. So again, looking back to our earlier lectures, this is also a very dynamically warm galaxy. Here we have an overview of the differences between fast and slow rotators. This is table 5.2 from the course book, which I have written into this slide here, but it's the exact same information. We can see that fast rotators are flattened by rotation, whereas slow rotators can also be flat, but they will be flattened by anisotropy. They will be flattened because they are triaxial ellipticals. Fast rotators are oblate spheroidals. They are basically, again, they are flattened by rotation, but they also have a large component of randomly oriented stellar orbits. They have more or less isotropic velocity distributions if we account for the rotation. and they are more flattened than slow rotators are. Fast rotators are lower mass and have diskier isophotes, where slow rotators have more boxy isophotes and are larger. Fast rotators have lower Sersic indexes or indices, so they are, again, in this way, more disk-like than the slow rotators, which have the classical Sersic indices of around 4. Fast rotators are coreless, slow rotators are cored. The fast rotators have lower optical luminosity, younger stars, no alpha enhancement, weak radio emission, weak diffuse X-rays, and no kinematically distinct core. Whereas slow rotators often can have the kinematically distinct core that we saw before, which was kind of either counter-rotating or rotating at an angle from the rest of the galaxy, and they will have stronger diffuse X-rays, stronger radio emission, and so on. We will get back to some of these things here at a later point when we're talking about the ISM of elliptical or early type galaxies. Finally, we know that there is correlations between the central velocity dispersion, and various galaxy properties. The central velocity dispersion correlates firstly with the age of the stars. So larger central velocity dispersion correlates with a higher stellar age, which should not come as a huge surprise if we think of it. And I will implore you to think of it so we can talk about it when we meet. Secondly, more metal-rich stars in an early type galaxy also will mean a higher central velocity dispersion. And that is, of course, also interesting to think a little bit about why that is. And finally, alpha enhancement. Galaxies with high central velocity dispersion also have a higher alpha enhancement than the ones with lower central velocity dispersion. And finally, if we look into stellar populations of early type galaxies, we know from our previous look at the mass and color diagram here that we looked at before, that there is what we call the red sequence and the blue cloud and the green valley. So what we know is that early type galaxies are, well, there's a big overlap, right? You can see that there's definitely not a clear-cut separation between the two populations of galaxies. But also, on the other hand, as a very strong statistical rule, early type galaxies are redder for sure, and also perhaps less predominantly, but still definitely true, they are also more massive than the late type galaxies. And so we can ask ourselves why bigger galaxies are redder galaxies, right? Why is this? And so there has historically been two main hypotheses trying to explain this. The first hypothesis that we can see down here is that massive galaxies are more metal-rich, and therefore they will also become redder. This will happen because deep potential wells will confine the metals. If they are more massive, it will be harder for metal-rich gas to be pushed out, to be puffed out of the galaxy, compared to if we have a lower mass galaxy with a more shallow potential well, such that the feedback from star formation will have a much harder time getting rid of metals in more massive galaxies than in less metal galaxies. This means, according to this hypothesis, that most massive systems are higher metallicity, and that is why they are red. The other main hypothesis says that the current star formation rate is low in bright galaxies, but is closer to the average in mid-sized galaxies, as we can see over here. And that means that the most massive systems are simply older, and that's why they're redder. So one says that they are redder because they are higher metallicity. The other says they're redder simply because they are older and therefore they're more massive and bluer stars are gone. Most likely, a little bit like in kindergarten, most likely both sides are a little bit right. Most likely both effects are contributing in this case. We can try and take some clues from spectroscopy if we take like an integrated spectrum of the stellar population in an early type galaxy. First of all, we can see that they are very, very faint towards the blue. There are no bright or hot young stars in these galaxies. This is not entirely true, but it's almost true. There are very, very few bright and young stars in these galaxies. There's quite strong absorption in magnesium and sodium here, which is something that only happens if there has been very little star formation in the last billion years or more. That means most of the R-band light comes from red giants and from asymptotic giant branch stars. We also know that the stellar population is metal-rich in these stars. They have gone through many cycles of star formation. Each of one has been enriching the interstellar medium more with these elements. So a little bit reminiscent of the Milky Way bulge or a typical spiral galaxy bulge, but not reminiscent of globular clusters, which are very metal poor typically. And finally, again, as we saw before, the biggest elliptical galaxies are older. They have higher metallicities, or more likely, actually, both of these. That's it for now. Thank you so much for staying with me through this kind of long lecture, and I will be seeing you in the next one. Bye.